our last topic today, D.2, Introduction to Brute Force Method. Actually, at this point, we have learned this method several times. But here we just do the summary quickly, because the basic properties we have learned. So nothing new here. All right. Description of the brute force method. Properties of the brute force method. It is a straightforward method. And we do not need to apply any special techniques. If you apply some special technique, then we won't treat it as a brute force method, right? Because then some advanced features you will use to make the algorithm better. So when we talk about brute force method, so we do not use any relatively advanced technique. You can always apply it to a problem because it's so simple. I mean, just straightforward, and you do not need to do any special arrangement. So you can apply it anytime. And but if you do in that way, you should not expect to get a good solution in general. It's very rare you can get a good solution for a non-trivial. So here, when we solve a non-trivial computing problem, so usually, you cannot get the best solution by the brute force method. But it has its value. So here, although we do not expect to get a good solution from it, but there is some reason. Because we use it as the starting point. At the beginning, we do not understand the problem. We know for the problem solving, the understanding part is very important. But you need to, examine the problem, study the properties. So you need to do a lot of things in order to understand the problem, right? But before you have any good understanding, the brute force method is the easiest one. You can start working. That's why it is our starting point. That is our first try. It's our first try. And we can collect experience when we do it. And we can build up our experience. So we can understand the problem better and better. All right. The efficiency difference between the brute force method and a more advanced algorithm could be huge. We have example. So in Module 1, Part B, the polynomial evaluation problem, we compare it. The difference is huge, right? At the end, so I did one special example when n equals 1 million, right? 1 million. The comparison result as big as 1s 1 second versus 5.8 days, right? Huge difference. The brute force method, we need 5.8 days. And Horner's rule method, we need 1 second. Doing the same thing, the difference is that huge. All right? Yeah. So that's our basic understanding of the brute force method. Next, let us work on our old problem, problem number 4, sorting. Yeah. But this time we revisit it. Yeah. So this is our second algorithm. The first one, selection sort. Yeah. Some of you may ask why we need to solve the same problem the second time. Yeah. So there are some good reasons. Yeah. So I will explain that. Yeah. First, let me give you the problem. I just copy the problem. Yeah. We need to sort a given array in ascending order. Yeah. All right. Now, let me answer this question. Why we need to solve it another time? Yeah. Yeah. So there are some good reasons. Yeah. Here I want to use a special view to understand this question. Yeah. All right. First, we take this view. We know when we solve a problem, and we need to use some special method, right? And the thinking methods that we use to solve computing problems are very valuable. The thinking methods are valuable. Yeah. The reason is simple, because we can apply certain commonly used thinking methods later on many other computing problems in the future. Yeah. All right. But the question is, how do you package those thinking methods, right? How do you carry those thinking methods? Yeah. Because they are not physical objects, right? Yeah. So you cannot do things like, putting physical objects in certain containers, and carry, somewhere. Yeah. So they are, some thinking ideas. Yeah. So although people can write documents, right? So describe the algorithm details and put it in the digital format and put in some digital media, right? Flash drive, carry that, right? Yeah. But here we think in this way. So one particular computing problem. So here it's for example, a sort problem. The sort problem, it's a problem. Yeah. This problem, there are several thinking methods we can use to solve it. Yeah. Based on different properties, from different angles, with different ideas, solving the same problem. Yeah. And all those problem-solving methods are very valuable, right? So we want to keep those valuable methods somewhere. Yeah. Here we just imagine. So this particular computing problem, we treat it as a carrier. Okay? So it's a carrier. We can use it to hold multiple problem-solving thinking methods. Yeah. In that way. Yeah. Yeah. All right. Yeah. So that's one special understanding. Yeah. All right. Yeah. And those thinking methods later we can borrow, right? Because that's our experience. Yeah. So our old experience, very important for us to solve new problems. Yeah. All right. Yeah. So it's important. Yeah. All right. Now, next, we want to work on this problem. Yeah. in order to find a new solution, so this time we want to change the view. The view should be different from the one we used the first time, specifically for that selection sort. Yeah. So this time we will use a completely different view on the same computing problem. Okay. All right. So the view based on a special property. So we need to discover some special property. Yeah. The property should be different from the one we discovered the previous time. Yeah. So completely new property. Yeah. So we should view this problem in a completely different way. Yeah. So let's see how to do it. Yeah. Let's make our observation. What is that property? Okay? We need to discover it. Okay? We need to do some quality observation on our current problem. Yeah. Here, let me just draw a simple diagram. So this is an array. Yeah. So we want to work on it. Yeah. But when we work on it, we want to study. We want to find some special property here. Yeah. All right. So let's try it. Yeah. All right. Let's pick two elements in this array. Yeah. 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 Later we want to consider. So in the general case, we want to consider arbitrary two elements in the array. Here, the diagram I show you here, two are the adjacent elements. Yeah. But we need to consider arbitrary two elements in the array. Yeah, the general case. The adjacent elements, that's a special case. Yeah, so we need to consider special case and the general case. Yeah. For the special case, then there is a, so here we need to study the order of these two elements, right? Yeah. Because our goal, we want to sort it in ascending order. Here, this word order is important, right? Ascending order. Yeah. So that order word is critical. So we want to study this critical word or this critical property here. Okay? All right. Then when we look at two particular elements here, then we can see there are basically two states. One is out of order, another is, in order, right? Yeah. Yeah. These two different states. Yeah. Between these two states, which one is our concern? Think about this question. Yeah. In order case, when these two elements are in order, that means in ascending order, right? So in ascending order matches our destination requirements, right? Yeah. There. These two, if we look at just these two elements, they are already in the ascending order. That means we don't worry about it. Okay? But our main concern when they are out of order, because it's not our desirable state. We need to change it. We need to change it from the out of order state to the in order state, right? Yeah. So that's our understanding. So we study this order, okay? So that means we should work on two elements that are out of order. So we study this property. This is our new view, okay? Yeah. Because in our first sorting algorithm, we didn't view the problem in this way. So this is a completely new viewing angle. Yeah. All right, so let's keep working on this direction, in this direction. Yeah. Observation for critical property. So now we want to make our critical observation here. Yeah. So look at this statement. If the array is not sorted, yeah, under this condition, what can we say? Yeah. So what we can say, look at this. There must be two adjacent elements that are out of order. Can you see that? Can you see this property? Yeah. So our assumption is the array is not sorted, not in ascending order. Okay, it's not ordered in, general case. Yeah. Under this assumption, we can say there must be, we can find two adjacent elements that are out of order. Can you imagine, can you, try to understand? Is it correct? If you feel it is correct, we need to explain why it is correct. Okay? All right. Here we need to, join some figure in our mind. That's our imagination. We need to use our intuition to understand the statement, this property. Yeah. Because here we can apply that contrapositive method. Contrapositive method. Okay? All right? So that is, we want to look at, so if the conclusion is not correct, so that means if this conclusion, there must be two adjacent elements that are out of order. We want to negate this conclusion. Negate. Yeah. We want to use a statement that is the opposite of this conclusion. Yeah. So there must be two adjacent elements. Then when we do the negation, for any two adjacent elements, they are in order. Okay? Yeah. That's the negation, right? So any two adjacent elements must be in order, right? Yeah. If that happens, yeah, because we do the negation, so we work on the conclusion first. That is the typical way for contrapositive method, right? So with this assumption, we can get the array sorted, right? Yeah. So here you need to do the imagination, okay? Any two adjacent elements in order. So the first two in order, right? Ascending order. Second two also in order. Then next two in order. All the way through the end in order. Then the whole array is in order, right? In ascending order. Yeah. That's our imagination. Yeah. But if the whole array is ordered, then the assumption is incorrect, because the assumption is, original assumption is incorrect. If the array is not sorted, not ordered. Yeah. So then that means our negation is wrong, right? Yeah, that's the essence of the contrapositive method. The negation is wrong, so this current version of the conclusion is correct. So we prove it. So we view in that way. Right? Yeah, so we get this property. So we understand this critical property. Here, I give you the reference in the textbook for this algorithm. Yeah. Next, then we need to do some further study. Yeah. Because here, when we select two elements that are out of order, this property has some special significance, right? In our current view, it has special significance. So we want to create some special concept to describe this special property. Here we use this inversion concept to define this special phenomenon. Yeah. That is a pair of elements, A sub I and A sub j. Here, these two elements can appear anywhere in the array. So it's a global pair, okay? Not a local pair. Not like these two pairs, it's a local pair. So here we're talking about a global pair. Yeah. It's called an inversion. We mean on this condition, the following condition should be true. So if I less than j, yeah, their subscripts, the subscripts of these two elements are in ascending order. Yeah, I less than j, ascending order. But their values are in descending order. Yeah, so the direction is opposite. So the direction of the subscripts is opposite of the direction of their corresponding two values. Yeah, so that's why we call it inversion. Yeah, this concept. Yeah. After we define this concept, then we can use this concept to characterize, to describe, to understand the whole problem. And our new algorithm will be built on top of this new property. Yeah. All right. So then, with this inversion concept, now we want to modify our old version of the critical property. This time, we can use the inversion concept to describe our previously viewed critical property. Yeah. So let me use two versions to, show you that observation. Yeah. The first version, if the array is not sorted, yeah, then there must be an inversion. Yeah, so that's the first statement. There must be an inversion. So here the inversion, any inversion, right? So there must be an inversion. Yeah. Here this inversion we mean the global inversion. Yeah. Global inversion. Yeah. So like this. So this is global inversion. Okay? Yeah. So if it's not sorted, there must be an inversion. So how to see that? So if you want to see that, you can use the contrapositive method. Contrapositive. So if you negate the conclusion, then if there is no inversion, no inversion anywhere, yeah, so then you can see, so the imagination like this, no inversion, right? Any two adjacent elements, it's not inversion, so ascending order. Next two adjacent elements, no inversion, ascending order, and so on, all the way to the end of the last two elements, two adjacent elements. Yeah. So you can imagine in that way, right? Yeah. But the next statement I want to emphasize, so I want to modify this current statement in slightly different version to expose the critical part. Yeah. But they're equivalent. So, but I want to use a, better way to write this statement. So that is, if the array is not sorted, there must be an adjacent inversion. Adjacent inversion. Yeah. So from the global inversion, this is a global inversion. Okay? Global inversion view, now we change to adjacent, that's the local inversion, right? That change, right? That change is a better version, yeah, because when we only need to work on the local inversions or adjacent inversions, we can reduce our work, right? Yeah. Because global inversion, there are too many global inversions. Yeah. If we narrow down to local inversions or adjacent inversions, well, adjacent inversion is stronger than local inversion, right? Yeah, local, just some rough description, adjacent, so we know, yeah. So the most local case, right? Adjacent, that's the most local case, yeah. All right, yeah. So here you can see with this last statement, that's our best description for the critical property that we observed for this particular problem. Yeah. All right. Yeah. So, yeah. So later you will see this kind of from global view to local view, this approach, this is another general problem solving approach. Yeah. In problem solving, when we work on a global property, it's much harder than we work on local property. Yeah. Because the reason is simple. There are too many instances with satisfying the global property. Yeah. But for the local property, yeah, we can reduce the number of instances significantly. Yeah. So then we can reduce amount of work. Yeah. So that's the general understanding. Yeah. All right. So at this point, yeah, so we define the critical concept here, inversion concept. Then we use this concept to help us understand the critical property that we observed for this particular problem. Next, we need to work on the solution. Yeah. Yeah. So after this understanding step, next we need to do the work. Yeah. All right, so let me stop right here for today's lecture.